Let's get back in the vibe of this.
The possibilities of what may happen in the experiment. Okay, so let's start with our agenda. The first piece in a probabilistic model is a description of the sample space of an experiment. So we do an experiment, and by experiment we just mean that just something happens out there. And that's something that happens. It could be flipping a coin, or it could be rolling a die, or it could be doing something in a card game. So we fix a particular experiment, and we come up with a list of all the possible things that may happen during this experiment. So we write down a list of all the possible outcomes. So here's a list of all the possible outcomes of the experiment. I used the word list, but if you want to be a little more formal, it's better to think of that list as a set. So
it's like a set of all possible outcomes. So if you're like flipping a coin, it's like the set of all possible outcomes is like heads and tails like this. Like, so this is an outcome, and this is an outcome.
have a set. That set is our sample space, and it's a set whose elements are the possible outcomes of the experiment. So for example, if you're dealing with flipping a coin, your sample space would be heads, this is one outcome, tails is one outcome, and this set, which has two elements, is the sample space of the experiment.
It's kind of weird to view the sample space like that. Usually don't kind of do it like that. It's almost like you have a discrete sample space where you have these kind of like square things. You have like heads and tails, or you have like a continuous sample space where you've got like, I guess this is the event heads, and like this is the event tails. And kind of more accurately, it would kind of be like split in half, like heads and tails like this. This is the event that heads happens. This is the event that tails happens. You can kind of also view it like it's kind of a few events. There's like the set with heads in it. It's like the set with tails in it, the event. There's the event, there's nothing in it. And there's the event, heads, tails like this. What is probability again? Is it the probability of an event happening? It's like if you said like the probability of like heads, tails right now, it's not intuitive to me what this means. I guess it's 1. So it's like, what's the probability that heads or tails that happens? What's the probability that the outcome of the experiment is in this event? What's the probability of this event happening? And so what's the probability of an event? Probability of an event is the sum of, I guess, all the little, I guess we'll say all the outcomes in E. The probability of, I guess it's like the singleton set of that outcome like this. So we just kind of sum up all the individual, we sum up all the singleton sets. So the probability of heads tails is equal to the probability of heads plus the probability of tails, which is equal to 0.5 plus 0.5, which is equal to 1. Just always wind up getting confused between an outcome and an event and the sample space. Sample space is like omega, an event, maybe that's x, maybe an outcome is little x. Yeah, we'll see. I really want to understand this stuff on like on just like the level of freaking like algebra or like arithmetic or positive and negative numbers, where you can just look at any arithmetic expression, algebraic expression, like 5x plus 2 or something. Maybe that's kind of like a bad example. It's like yeah, I guess it's maybe almost like this. It's like fractions. It's like 5/3 plus 2 or something. And you kind of just like know that, this is a number and this is a number, and any number, times 1 is equal to the number. So you can, multiply this thing by 1 and this thing still like holds, and like 1, another way to write 1 is 3/3, and kind of like another way to write 2 is 2/1. And when you're multiplying two fractions, I don't really know a good way to even intuit this, but I just know you can multiply the numbers on the top and the numbers on the bottom. Like 2 times 3 over 3. I don't know how to show that other than you just try and do it and you see that it works. Yeah, and I really thought about kind of like an intuitive way to know that this is basically true, that you can do this. It's really weird because 2 is almost like, I don't know, you have like 2 full kind of blocks here, and then 3/3, it's kind of weird. You kind of have to like decide on what is the size of 1 that you want to decide on. So you have like 1 and 1 here, and so you have like 2 of these things. Whereas here you have, you just have 1, but you kind of split this into thirds. It's like 3/3. It's 2/1. Yeah, I don't even really know how to like intuitively justify this step here. Interesting. Okay. Anyway, that's basically my goal for taking this course. Like, I just want to understand at like such like a deep level, like, yeah, where any probabilistic like expression or equation that I see, that I'm able to just break it down into its constituent parts and just kind of like know how to manipulate, I guess, know the laws of probability like so well that, yeah, I can just take any expression and manipulate it and massage it into a way that kind of makes sense.
Okay, what do we need to think about when we're setting up the sample space? First, the list should be mutually exclusive, collectively exhaustive. What does that mean? Collectively exhaustive means that no matter what happens in the experiment, you're going to get one of the outcomes inside here. So you have not forgotten any of the possibilities of what may happen in the experiment.
Just that like collectively exhaustive thing, like you just have like one set and you just got a bunch of elements in the set. And so, you have this sample space. Sorry, it feels like a little disrespectful to write over this guy. So you've got your sample space. And I guess you've got your probabilistic experiment, which is like it's just really weird to think about this stuff on just like the kind of most fundamental level, which is, you've got your probabilistic experiment, and this just outputs I don't even know. This outputs like a box, This is just a thing in the real world. It's like a phenomena. And like we are kind of reliable enough. Like this is supposed to be an eyeball. We just kind of like take this and filter it through our eyeballs and kind of map this to an outcome, which is like, heads or tails. There's in real life, there's just like this coin that, it turns up H, or it kind of like turns up tails, and you can see that and process it consistently enough to map it to an outcome. And that outcome is heads or tails. And so like that outcome should be, in this set. We've got this heads thing here, which is, you can think of it as a singleton set. You got this tails thing. This tails thing here. Be another singleton set. So you kind of take the real world and you map it to this like mathematical object. It's just this like symbol. You map it to this symbol. It's like in Ruby, they have symbols like H. I don't know how you define that, but it's just crazy, man. So when he says mutually exclusive, he's like, you have your experiment, you map that to an outcome, and that outcome has to be in the sample space. It's got to be an element, because you can write down the sample space like this, assuming that we're talking about like accountable, whatever, finite kind of sample space to keep it simple. Got like the first outcome, you've got the second outcome, you've got the third outcome, you've got n outcomes, say. And so the outcome, you got to be able to like point to one of these elements like in the set and say, yeah, that outcome is this. It's like, you've got your first outcome, whatever it is, you've got a heads in there, you've got the third outcome, you've got, let's say you got tails here, and then you've got like the last one. You got to be able to like pick this out and say, yep, H is in there. You got to be able to pick this out and say, yep, tails is in there. And there you go.
Mutually exclusive means that if this happens, then that cannot happen. So at the end of the experiment, you should be able to point out to me just exactly one of these outcomes and say, this is the outcome that happened. Okay, so these are sort of basic requirements. There's another requirement which is a little more loose. When you set up your sample space, sometimes you do have some freedom about the details of how you're going to describe it. And the question is, how much detail are you going to include? So let's take this coin flipping experiment and think of the following sample space. One possible outcome is heads. A second possible outcome is tails, and it's raining. And the third possible outcome is tails, and it's not raining. So this is another possible sample space for the experiment where I flip a coin just once. It's a legitimate one. These three possibilities are mutual.
That's pretty interesting. It's like you've got kind of your experiment, you've got kind of your like coin here, and you've got, you know, heads, and your coin could also come up tails. But this kind of approach is almost like, you know, you kind of like it's almost like modeling the world, and like this is like the whole world, I guess. You've kind of collapsed like the whole world down to pretty much just this. You've ignored everything else like in the entire world, basically, other than, you know, this heads here. And but in this like tails like not raining case, you know, I want to kind of draw it like more like, you know, so you got your tails, you got your coin that came up, but you're also including kind of like this cloud outside here that's kind of like raining as well. And so you're kind of like taking into account like more of the world. Your aperture has widened to just be like aware of like the weather like around the coin. Your focus has drifted from just like myopically focusing on the coin to the surrounding environment, and you're taking that into account. It's a more inclusive sample space, but we're designing it to illustrate, elucidate, amplify, like magnify, just put our focus on this coin and really like nothing else. Like if all we really care about is like coin flips and the behavior of coins, and weather is not really pertinent to our concerns, then we can just like ignore all this and like just focus on the coin. So that's pretty crazy. This is pretty interesting too. It's kind of like this idea that you can like take a class like multiple times and kind of get more different stuff out of it each time you take it. Like how you can read a book multiple times and you focus on different stuff in the book. It's almost like you take this class multiple times and kind of go deeper and deeper, like every time into this class that you take it with like the basics, stuff that you glossed over the first time, just like wasn't interesting to you, or your awareness like just passed over it. You just weren't aware of it. The next time through, you've kind of like got more of the fundamentals down so you can pay more attention to the subtleties of kind of like what you're interested in. It's crazy.
Exclusive and collectively exhaustive. Which one is the right sample space? Is it this one or that one? Well, if you think that my coin flipping inside this room is completely unrelated to the weather outside, then you're going to stick with this sample space. If, on the other hand, you have some superstitious beliefs that maybe rain has an effect on my coins, you might work with a sample space of this kind. So you probably wouldn't do that, but it's a legitimate option, strictly speaking. Now, this example is a little bit on the frivolous side, but the issue that comes up here is a basic one that shows up anywhere in science and engineering. Whenever you're dealing with a model or with a situation, there are zillions of details in that situation. And when you come up with a model, you choose some of those details that you keep in your model, and some that you say, well, these are irrelevant, or maybe there are small effects, I can neglect them, and you keep them outside your model. So there's definitely, when you go to the real world, there's definitely an element of art and some judgment that you need to do in order to set up an appropriate sample space. So an easy example now. So of course, the elementary examples are coins, cards, dice. So let's
Coins, cards, dice. Coins. Heads versus tails. Cards. This is like the 5, like hearts. This is like jack, diamonds. You got coins. Cards. You got dice. There's 1, 2, 6 up here. Dice. Fundamental. Pedagogical devices. Giving simple examples, elucidating, illustrating deeper concepts.
with dice, but to keep the diagram small, instead of a 6-sided die, we're going to think about a die that only has 4 faces.
Here, sample space. Ways to draw the sample space. You can draw it as a grid, like this. You can draw it as kind of a Venn diagram, like this. Or I guess like as a Venn diagram, like this, the different elements in singleton sets. You can draw it as a Venn diagram, I guess where it's like just split in 2. You can draw it as a sequential decision process where outcome 1, outcome 2, outcome 3, outcome 4. In each case, the thing that matters is you're able to point to an individual outcome. You're able to identify them. Where are the outcomes here? This is an outcome. This is an outcome. Where are the outcomes here? This is an outcome. 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 That's an outcome. That's an outcome. Where are the outcomes here? This is an outcome. This is an outcome. This is an outcome. This is an outcome. Where are the outcomes here? This is an outcome. This is an outcome. Where are the outcomes here? This is an outcome. This is an outcome. This is an outcome. This is an outcome. In any depiction of a sample space, all you really need is just to be able to point to individual outcomes and say, that's an outcome, that's an outcome, that's an outcome. Any of these depictions have that property. It's an outcome. It's an outcome. These are outcomes. This is an outcome. It's an outcome. This kind of shows the structure of how the outcomes are created. Maybe just the structure of the outcomes. I don't know.
So you can do that with a tetrahedron, doesn't really matter. Basically, it's a die that when you roll it, you get a result which is 1, 2, 3, or 4. However, the experiment that I'm going to think about will consist of 2 rolls of a die.
Roll.
A crucial point here. I'm rolling the die twice, but I'm thinking of this as just one experiment, not 2 different experiments, not a repetition of twice of the same experiment. So it's one big experiment.
One experiment, roll the dice twice. So an outcome of the experiment is 1, 4. An outcome of the experiment is 2, 2. An outcome of the experiment is 1, 2. These are outcomes.
During that big experiment, various things will happen, such as I'm rolling the die once and then I'm rolling the die twice. Okay. So what's the sample space for that experiment? Well, the sample space consists of the possible outcomes. One possible outcome is that your first roll resulted in 2 and the second roll resulted in 3, in which case the outcome that you get is this one, a 2 followed by 3. This is one possible outcome. The way I'm describing things, this outcome is to be distinguished from this outcome here, where a 3 is followed by 2.
It's kind of interesting, again, like coming back to our example where, something happens in the world where there's literally like a dice here, and this dice was a 2, and then there's another dice kind of like right next to it, and say this is a 3, and there has to be some human, like, honestly, like a human judge that says like, oh yeah, the first one came up with a 2 and the second one came up with a 3. Even if like the orders are switched, this 3 is to the left, this 2 is to the right. The judge says, oh, no. Even though like 3 comes before 2, like I saw him roll the 2 first and then the 3. Yeah, the order doesn't matter. Like I saw him roll the 2 first. So yeah, it's still 2, 3. So you really need like a human judge to kind of give a thumbs up or a thumbs down and to kind of do this. Now, I guess this could be a computer system as well. It's like a computer vision kind of thing, some kind of like machine learning model, which does some classification. It like identifies the first one, identifies the second one, classifies this as a 3, classifies this as a 2, and outputs 2, 3. So it could be a I don't know how to draw this, like a computer webcam or whatever. Camera. Yeah.
Backgammon, it doesn't matter which one of the 2 happened. But if you're dealing with a probabilistic model that wants to keep track of everything that happens in this composite experiment, there are good reasons for distinguishing between these 2 outcomes. I mean, when this happens, it's definitely something different from that happening. A 2 followed by a 3 is different from a 3 followed by a 2. So this is the correct sample space for this experiment where we roll the die twice. It has a total of 16 elements, and it's, of course, a finite set. Sometimes, instead of describing sample spaces in terms of lists or sets or diagrams of this kind, it's useful to describe the experiment in some sequential way. Whenever
It's kind of interesting that he mentioned lists and sets, and now we're talking about trees. It's just kind of interesting. I don't know if it's a coincidence that in computer science, like lists and sets and trees are like very core and fundamental data structures. It's like how do we encode the sample space? Do we encode it as a list, as a set, as a tree? It's kind of weird because here in computer science, we often do this. We often, but not always, do it because for efficiency. But sometimes we do it also for, understandability. I would say more commonly, it's kind of like readability. Whereas like this is purely for, understanding pretty much. Interesting. Wonder if these two are in tension. I don't know.
you have an experiment that consists of multiple stages, it might be useful, at least visually, to give a diagram that shows you how those stages evolve. And that's what we do by using a sequential description or a tree-based description, by drawing a tree of the possible evolutions during our experiment. So in this tree, I'm thinking of a first stage in which...
Almost like you're factoring the thing, like, it's almost working backwards kind of thinking. Like you get the outcome 2, 3, and you're like, oh, how did you get this? Well, first you rolled a 2 and then you rolled a 3. And you can kind of do that for every single one. You roll a 2 and then a 2, you roll a 2 and then a 1. You could roll like a 3 and then a 1. You could roll a 3 and then a 2. Kind of some more. Kind of like unpacking the structure of this. Kind of expanding or exploding it out, revealing more of the structure of the dynamics that led to this thing that we see.
We roll the first die, and there are 4 possible results, 1, 2, 3, and 4. And given what happened in the first, let's say in the first roll, suppose I got a 1, then I'm rolling the second die, and there are 4 possibilities for what may happen to the second die, and the possible results are 1, 2, 3, and 4 again. So what's the relation between the two diagrams? Well, for example, the outcome 2 followed by 3 corresponds to this path on the tree. So this path corresponds to 2 followed by a 3. Any path is associated to a particular outcome. Any outcome is associated to a particular path. And instead of paths, you may want to think in terms of the leaves of this diagram. Same thing. Think of each one of the leaves as being one possible outcome. And of course, we have 16 outcomes here. We have 16 outcomes here. Maybe you noticed a subtlety that I used in my language. I said I roll the first die, and the result that I get is a 2. I didn't use the word outcome. I want to reserve the word outcome.
Wow, you're so precise.
To mean
the
overall outcome at the end of the overall experiment.
Can't rewind this crap? with the
So
left.
2
It's weird.
outcome. And of course, we have 16 outcomes here. We have 16 outcomes here. Maybe you noticed a subtlety that I used in my language. I said I roll the first die, and the result that I get.
Result. So these are like, so you said results. These are like intermediate results, maybe. Intermediate results. And these are outcomes. And these would be, this is an intermediate result.
Is a 2. I didn't use the word outcome. I want to reserve the word outcome to mean the overall outcome at the end of the overall experiment. So 2,3 is the outcome of the experiment. The experiment consisted of stages. 2 was the result in the first stage, 3 was the result in the second stage.
Yeah, intermediate results. So like these are intermediate results, and like these are intermediate results. Factoring this thing, 2, 3, this is the outcome. And so like this thing here is in intermediate result, and this thing here is in intermediate results. Intermediate result, outcome.
Put all those results together and you get your outcome. Okay, perhaps we are splitting hairs here, but it's useful to keep the concepts right.
No, this is like, this is perfect. It's amazing.
What's special about this example is that besides being trivial, it has a sample space which is finite. There's 16 possible total outcomes.
Outcome. 16 possible total outcomes.
Every experiment has a finite sample space. Here's an experiment in which the sample space is infinite. So you're playing darts, and you put all those results together and you get your outcome. Okay, perhaps we are splitting hairs here, but it's useful to keep the concepts right. What's special about this example is that besides being trivial, it has a sample space which is finite. There's 16 possible.
I didn't even realize this whole time that these were the same sample space. It's just like two different ways of writing the same thing. That's so great. Here's like another way of doing it too, where you've got, these, you don't have to like draw the singleton sets, but you can say, yeah, we've got 2, 3 as an outcome. We've got 3, 2 as an outcome. We've got, 1, 4 as an outcome. We've got 2, 2 as an outcome. So you can, got 1, 3. So you can go in here and you can point to, this is an outcome. So you've got sort of 1, 2, 3, 2, 3, 2, 3. So like this outcome is the same as this outcome, which is the same as this outcome. These are all different ways to just be able to point to the same outcome. Different representations pointing to the same thing. Any other way? I don't think so. It's basically he talked about lists. I mean, I guess that's another way to kind of do it. A list, a set, I'd say the list and the set are kind of the same thing. So you basically say the set is, say we got 2, 3 in here. Let's see, we got 1, 3. Let's see, we got 2, 2. And so this is yet another same outcome here. He said list slash set trees. So like this is the tree right here, the list set thing. This is a set. This is kind of geometric set. This is kind of another set, maybe. Like these are the main two. Hash table. Getting all computer science.
Outcomes. Not every experiment has a finite sample space.
Can I rewind?
Here's an experiment in which
that's on the phone where you double click and it rewinds
the sample
10
space
seconds.
is infinite. So you're playing darts.
Sample space is infinite. So this is almost kind of like a set where every like point is in there. Another infinite set would kind of be like when you've got, the first outcome, the second outcome, and it just kind of goes on forever. It's kind of even weird to like write this closing curly bracket because it kind of implies that, this thing, you can kind of stop it. It's almost kind of like you should leave it off. It just kind of goes forever. It's weird. So yeah, the set, we have the tree. Yeah, it doesn't really make sense to like factor this out into intermediate results. You could, but it's not very intuitive. So you've got like a tree that's kind of like another way. The list set tree.
The target is this square, and you're perfect at that game, so you're sure that your darts will always fall inside this square. So, but where exactly your dart will fall inside that square, that itself is random. We don't know what it's going to be, it's uncertain. So all the possible points inside the square are possible outcomes of the experiment. So a typical outcome of the experiment is going to be a pair of numbers, x, y, where x and y,
for example, an outcome,
real numbers between 0.
For example, an outcome is like 0.5, 0.5. That's an outcome. It's like 0.5 and 0.5 here. This pad really has a problem with dots that are close together. 0.5 and 0.5. That's an outcome.
Now there's infinitely many real numbers. There's infinitely many points in the square. So this is an example in which our sample space is an infinite set. Okay, so we're going to revisit this example a little later. Okay, so these are two examples of what a sample space might be in simple experiments. Now, the more important order of business is now to look at those possible outcomes and make some statements about their relative likelihoods. Which outcome is more likely to occur compared to the others? And the way we do this is by assigning probabilities to the outcomes. Well, not exactly. Suppose that all you were to do was to assign probabilities to individual outcomes. If you go back to this,
wow, yeah, that's a really good point.
Example, and you go back to this example, it is likelihoods. Which outcome is more likely to occur example, and you consider.
Hey, it's working again. Okay, cool.
If you go outcome, let's say this point.
Yeah, man, just thinking in terms of outcomes. So thinking in terms of outcomes is basically sufficient in the discrete case, but if we're just thinking in terms of outcomes in the continuous case, you're not going to do anything useful. Like for any point here, 0.5. This is going to be 0. So you're just going to go through, hand wave and say enumerate all the points. And basically you've just got like the probability of every outcome. The probability of every outcome is equal to 0, where outcome is a member of the sample space. Maybe that's a better way to do it. So you've basically just like done this. And, you want to say, all right, I defined the sample space, but it's not interesting, it's not useful, and it's not even a proper sample space. So this isn't sufficient. That's weird because like in the dice case, you want to just kind of like split everything up and be like, yep, probability this, probability this, probability this, probability this. And that is sufficient. But it's almost like in the discrete case, you can't even do that. Like you have to be like, all right, the probability of these 3 events, probability of like these 3 events, these 3 events, and so like what's the probability of these 3 events, this kind of like area, and what's the probability of these 3 events, and what's the probability of these 2 events, and what's the probability of this kind of whole thing here. And that's how you're kind of like defining it. You're defining it in terms of sets, non-singleton sets. And what's this one here? Well, this one would be 0 kind of in the continuous case. Crazy.
To individual outcomes. If you go back to this example and you consider one particular outcome, let's say this point, what would be the probability that you hit exactly this point to infinite precision? Intuitively, that probability would be 0. So any individual point.
By the way, that's not intuitive. By the way, like intuitive point with infinite precision. I don't know. I mean, it is. It's not as intuitive as he says.
In this diagram, in any reasonable.
I would say it's a very, very small number. I would say it's like.
Should have 0 probability. So if.
Basically say like. I basically say, if it's this point he's talking about, I basically say the probability of hitting, say this is like 0.3, 0.2. I basically say it's like epsilon, where epsilon is basically like 0. It's like so small. It's like 10 to the negative like 200 or something crazy small like that.
In any reasonable model should have 0 probability. So if you just tell me that any individual outcome has zero probability, you're not really telling me much to work with. For that reason, what instead we're going to do is to assign probabilities to subsets of the sample space, as opposed to assigning probabilities to individual outcomes. So here's the picture. We have our sample space, which is omega, and we consider...
It's almost like when you're doing that in the discrete case. Yeah, I mean, this is kind of going back to the singleton set thing, but so if you've got kind of like three-sided die, you consider each of these as like a singleton set. That's kind of like implicitly what you're doing. I wonder if there's like an equivalence with something in programming where you kind of wrap more primitive data type in some container thing. Like there's kind of this like maybe data type thing where you kind of wrap like an int, maybe wrap like an int in a maybe. I think it was better before. Fine, whatever. Int, maybe an int, and this is kind of like, it's almost kind of like a box where this is kind of like the int is in here and there might be like nothing in the box, or there might be like I in the box. I don't know, could be. It's almost like here, you're just taking the primitive thing and you're wrapping it in this set.
Some subset of the sample space, call it A, and I want to assign a numerical probability to this particular subset, which represents my belief about how likely this set is to occur. Okay, what do we mean?
So yeah, when you're defining the probability, what did he call it? Like the probability rule, or like the probability? This, I think we're just talking about sample spaces right now.
And I'm introducing probability to this particular subset.
So he's talking about assigning probabilities now. Okay.
Which is omega. And we consider some subset of the sample space, call it A. And I want to assign a numerical probability to this particular subset.
So yeah, it's kind of like when you have a continuous sample space, you have to figure out how to like partition up the sample space and assign probabilities to them. This is like this, for example. It's got to sum up to 1.
Which represents my belief about how likely this set is to occur. Okay, what do we mean to occur? And I mean,
to occur, yeah, an outcome is in that thing.
Using here a language that's being used in probability theory, when we talk about subsets of the sample space, we usually call them events as opposed to subsets.
So just kind of like thinking about how we kind of even got here, it's like we started talking about experiments and outcomes. So we started talking about outcomes, and now we're talking about probability. And now we have to talk in terms of events. We didn't need to like introduce concept of an event until we started talking about probability. As long as we're just in the domain of talking about experiments, we can talk about outcomes and we're good. We don't even need events when we're kind of at this point. But once we start talking about probability, we're talking in terms of events. And, events are kind of, I don't know how you say it's that they're like defined in terms of outcomes. They're like you kind of have to like figure out your outcomes first, and then like they're defined in terms of events. Kind of define them in terms of events. Yo, I can't.
The reason is because it works nicely with the language that describes what's going on. So the outcome is a point. The outcome is random. The outcome may be inside this set, in which case we say that event A occurred.
This is really I'm gonna have to do this like so many times. Like really to say like the probability of an event happening is just like one of the outcomes in E happens. This for some reason is very unintuitive for me. The event occurs. The outcome happens. So it's almost like before we were talking in terms of, all right, we define the sample space and we need to be able to like the probabilistic experiment happens and we get an outcome and we need to be able to point to one event in here and say, yep, that's the event. It's almost like in a similar way, if we partition up the sample space into events, then when the outcome happens, we need to be able to pinpoint the outcome and say it's here, and oh, by the way, it's in this event right here. So the event kind of forms this like enclosing container around the outcome, and that event occurs if the outcome is in it.
If we get an outcome inside here, or the outcome may fall outside the set, in which case we say that event A did not occur. So we're going to assign probabilities to events. And now, how should we do this assignment? Well, probabilities are meant to describe your beliefs about which sets are more likely to occur versus other sets. So there's many ways that you can assign those probabilities, but there are some ground rules for this game. First, we want probabilities to be numbers between 0 and 1 because that's the usual convention. So probability of 0.
I think maybe I'm getting towards the end of this stream. I don't know. We'll see.
Means we're certain that something is not going to happen. Probability of 1 means that we're essentially certain that something is not going to happen. So we want numbers between 0 and 1. We also want a few other things. And those few other things are going to be encapsulated in a set of axioms. What axioms means in this context, it's the ground rules that any legitimate probabilistic model should obey. You have a choice of what kind of probabilities you use, but no matter what you use, they should obey certain consistency properties, because if they obey those properties, then you can go ahead and do useful calculations and do some useful reasoning.
All right, I think I'm gonna bail on this stream, guys. Yeah, this is crazy. Yeah, that was a good time. Yeah, we'll see. We'll see about yeah. Thanks guys for joining. We'll see you later. Peace.